All right. I think I'm going to get started then. Hi guys, I'm Evan Deutsch, and I'm going to give a quick talk or brown bag on MPC control. Just preemptively, if you guys have no idea what that it means, it's essentially a control algorithm. There's different kinds of MPC controllers, but in general, it's a control algorithm that updates every time step when you're driving around the track. It will map out different possible trajectories for your car. It will run them under an optimized cost function, and optimally choose the best one based on the error of the location of your car and what's in front of you, obstacles, barriers, speed constraints, bunch of different variables. And every time step it'll update and draw a new path and then give you an input, and that will essentially allow you to optimally drive your car in a changing environment continuously. So it's a very efficient algorithm. Most it's one of the best and probably fastest and most efficient algorithms for autonomous driving and especially autonomous racing. So it's definitely a good thing to learn about. And you can go to the next slide and I can get more specific. So MPC is a multivariable controller. That basically means that instead of having to calculate a steering angle and a throttle value for your vehicle that you're trying to drive autonomously separately, the algorithm can actually do it together and optimize them in tandem. So that's a pretty big advantage of using MPC, and a big reason why it is so efficient and well used. It can handle constraints, which is part of how it models its optimization function and how it solves a cost function. It will check those trajectories that you can kind of see a visualization in the bottom right where a car is mapping out a bunch of different possible trajectories. It'll go through them and say there's a vehicle that one of the trajectories goes over. A constraint would be that you couldn't go through a vehicle or another vehicle or an obstacle. So based on constraints, it would eliminate that choice and then run an optimized function on the rest of the paths that follow the rest of the constraints and then choose the optimal path. It can also see, I already explained the future trajectories of the car. It uses physics and a dynamic physics model. You have to have a pretty flexible model of the car and be able to predict what's going on to be able to run MPC most efficiently.
Evan, you're muted. I don't know if you knew that.
I had no idea that I was muted.
You just muted maybe like 5 seconds ago.
Oh, really? I didn't click anything. Sorry. All right. Where do you want me to go back to then? I'll just restart this slide, I guess, because since we're recording it. My bad. Okay. I didn't know I'm muted.
No,
so, sorry.
I think we only missed like the last sentence you were saying.
All right, sounds good. Now I'll just go back to where I was starting. I think I was talking about how it's a dynamic physics model. So essentially, MPC uses a dynamic physics model to solve its cost function and choose the optimal path. That's basically pretty important, and it's kind of differentiates it from other kind of path planners or controllers that won't take into account like slip angle and like the tire, like basically friction and a lot of different other physics of the car. And then as I was saying before, it repeats every time step, which is the most important part. It will I'll get into more specifics as we go through, because I'm going to talk about each of the different like parts of an MPC controller and what it requires. But in general, the biggest reason that it's so efficient is because every time step it will figure out theoretically the most optimal control path, and instead of trying to follow it, it will do the first control input of that path and then calculate another path right after. So it's always doing the most optimal movement in the next step of time to basically plan its path continuously. And that'll be the biggest advantage, and I'll make sure to explain that in a clear, more concise way later in this presentation. So that's it for the introduction, and then we'll get into a little bit some more specific aspects of it next. You can go to the next slide. So these are the design parameters of MPC. I'll get much more into the specifics of them as we go in. Each of the next slides will basically be each of the parameters, but sample time is very basically the amount of time it takes to run each time step of your algorithm. Each time you run the algorithm, it'll probably take a different amount of time. So you want the sample time to be greater than the maximum amount of time that your algorithm takes to run, but you don't want it to be too long so that you can't react in time to different changes in the environment. So that's something I'll get more into. Prediction horizon is essentially your look ahead distance, where you can kind of see in front of you a certain distance, and you plan a path a certain distance in front of you. And the prediction horizon, if it's too long, your path might be you might be using too much memory. But if it's not long enough, you might not be able to see as far. It's basically your perception of the environment and what your algorithm is running that through. Again, we'll get more specific into all of these. Control horizon is the amount of future inputs that you're planning. And constraints, I've already kind of explained. It's the boundaries of what you can and can't do. They might be speed, obstacle, boundaries of the track, etc. And then the weights, there's a lot of different things like difference in the steering angle, maximum speed, a lot of different things that MPC might want to optimize for, and you can weight them differently. And when you run the cost function, and weights kind of tell you how important each thing that you're trying to maximize for or minimize is, and will allow you to pick the path accordingly. So that's pretty much it, and then we'll get more into each specific item now. You can go to the next slide. So sample time is probably the first thing you want to plan out. I've kind of explained it a little bit, but again, the algorithm time differs each time you run it. You want to choose the sample time that is the right number. If it's too large, then your sample time your algorithm's going to run too slow. It's going to have to wait too long for each iteration. So say you run your algorithm, you decide to move a little bit to the left to go to the optimal trajectory. You do that, and you want to run your next algorithm at your next time step, but your sample time is large because your algorithm's inefficient, and your car can just drift your car can kind of drift, and then the next time you run your algorithm, your car is in a different spot than you want it to be, and it'll always be trying to catch up. So you don't want it to be too large. You don't want to have a low reaction time. That kind of means if it's also too large, and say a car swerves in front of you, but your sample time is so large that you don't have time to react. You want to be able to react instantaneously to movements like that, or nearly instantaneously. So you definitely don't want to have too large of a sample time, but you need to also be careful that it's not too small, because if it's too small, you might not have time for your algorithm to run. And if it's too small and you still have time for your algorithm to run, it might put too much stress on whatever hardware you're using, and it might be too computationally demanding. So you need to find a happy medium there, and that's kind of a common theme with MPC, with all these different kind of parameters and design parameters that you're choosing. You gotta basically weigh costs and benefits and try to find the right balance for each thing. So that'll be common for each of the parameters I'm about to explain. And then I'll go get into prediction horizon controller next. So prediction horizon is, like I said before, you can kind of see on the bottom that length is how far your car can see and how far it'll plan the path. So even if your actual hardware on your car allows you to see further, you're not going to want to make your prediction horizon that the entire length that your car can see, because that will be very limiting, and will lead to you creating giant paths at every time step, and your algorithm won't run effectively, and you generally don't need to plan your path too far ahead when you're running it every time step, because remember, you're only including the first control input into your algorithm, and then you're just repeating the process. But you also don't want the prediction horizon to be too short, because as you can see in this picture below, say the prediction horizon went up to the point right before the truck, you wouldn't know there's an obstacle in front of you, and your algorithm would still run you closer to the car. And then by the time you saw it, you'd have to probably brake and swerve out of the way. So you want to be able to see comfortably in front of you in order to see obstacles and different unpredictable things. But you also don't want it to be too large as to unnecessarily use memory and waste time and efficiency of your algorithm. So again, keep balancing. You keep having to find a happy medium with these things, but that's kind of the thought process when it comes to prediction horizon. And next, I can get more into control horizon. It's a little confusing to understand conceptually the difference between the control horizon and the prediction horizon, but I think that it is pretty evident in the picture above, so I'll try to explain it. So the control horizon, as opposed to being the path that you're planning across a different horizon, it's the number of steering angles that you're kind of planning. So if you can see on the top, you always want your control horizon to be shorter than your prediction horizon, which is really confusing, but there's a very specific reason for that. If you can see in the top picture, the control horizon is shorter, and that is because the predicted output, which is essentially the path that you're planning, goes across the whole prediction horizon, and it leads you to an optimal direction. And that optimal direction essentially is the path you're trying to follow, and based on the prediction horizon that you chose, not too large, not too small. And the reason that you don't need all the control inputs up to the end of that is because the control inputs at the beginning are the ones that you choose, that basically correct your path to the right location. And then after your path is like corrected and you're on that path, the control inputs become smaller and less important. And at the same time, a second reason is, like I said before, for the MPC, you're running the control algorithm, and then you're getting all this control horizon that you're calculating. You're getting a variety of steps, and then you might try to optimize it by first seeing, okay, how far off from the optimal path is my prediction horizon path. Like that's how you might. You're the whole goal of this is choosing a path, an optimal path based on the trajectories that you planned before. So you can try to figure out, okay, is this path have a minimum curvature? Is it in the right location on the track that we want it? You can kind of find errors. You can see in the bottom right picture, those lines from the green line, that's the error of your predicted path that you're kind of testing, quote unquote, and you're going to plug that into those errors into the cost function to try to figure out if that path really is optimal. But the reason that you don't need as many control inputs is because you don't need the difference between every control input at every step. You're only going to use the first one. You don't want to steer too harshly. So that's something you might consider. And that's why we need some control inputs. But the first ones are basically the most important ones. The smaller, the better for the control horizon. We want it to help make our algorithm more accurate and make the steering angles not too steep, because that will cause slip and will be uncomfortable for a driver if you're not racing. Say you're just doing like you're trying to make a self-driving car, like for Tesla. You don't want to make the steering angle too harsh. So that's definitely a factor we should consider, but it's not as important to consider as big of a horizon of those inputs. So that's kind of the reason the control horizon is shorter, but it's still factored into the cost function in the same way that the prediction horizon might be. So that's pretty much the thought process behind that. And we can continue on to the constraints now. So after you plan out your prediction horizon and your control horizon, you now have a platform to basically plan a bunch of paths, look into each path, figure out the error based on your control inputs to each path that it would require, and the actual paths themselves based on whatever you're kind of comparing it to. Again, MPC is a flexible algorithm. You can create it. You can use this strategy to essentially maximize and minimize for different things with different weights, which I'll explain next. But basically, now that you have that platform, you're going to want to be able to rule out paths that just don't satisfy the constraints of your car. Now, something that isn't too intuitive, but is very important when understanding model predictive control, is the difference between hard and soft constraints. So a soft constraint is a constraint that you want to keep on your car. You'd like say that you're driving up a hill, like in this bottom picture here, and you don't want to exceed 55 miles per hour because that's the speed limit. Now, if you made that a hard constraint and then you tried to drive up the vehicle, a naturally hard constraint, I think it's pretty intuitive to understand this, would be how hard you can press down your gas pedal. If you can picture that, you can only press your gas pedal so aggressively. So anything past that, you can't press the gas pedal through the floor of your car. So anything past that is a hard constraint. You cannot do that, but you theoretically can go above a certain speed limit. So if you're going up a hill and you're pressing the gas pedal as hard as you can, if you may, your car is going to lose speed if the hill is steep enough. And if you have a hard constraint that says your car can't go, say, below 45 miles per hour, you could find yourself in a position where you can't satisfy either of the hard constraints. And now you're in a situation where you can see here, I put it in quotes, an impossible situation, and your car will not know what to do and they will not find an optimal path. We need to avoid any situation where the car cannot find an optimal path. So we need to make some of the constraints soft. So essentially what a soft constraint would do in this situation is you'd apply it to the minimum speed of 45 miles per hour and you'd make that soft. So in all other non-edge cases, your car would make sure not to go below 45. But if you need to go below 45 in order to satisfy the rest of the hard constraints, it will do so, and your algorithm will still be able to run. So you have to keep that in mind when you're creating constraints for your vehicle. But the constraints allow you to rule out paths that are impossible. As long as they're not all impossible, it's a good tool to, one, if you do it correctly, make your algorithm more efficient so it doesn't have to check every path because some of them are not possible given the constraints you set. And two, it makes the algorithm, it's a very easy way for MPC to allow you to basically work with your paths and efficiently choose optimal and viable solutions. So it's a very important part of the algorithm. And then last, we'll go into what weights essentially means more specifically. So in the picture above, it's gonna, if you were confused on what I was saying between the difference between the errors of a prediction horizon and the control horizon, and then kind of minimizing the error when you're combining them with the cost function. If all that confused you, this might clear it up a little bit. In the top picture, you can see two different goals that we want to achieve. We want to have as little of a control difference between two inputs. So we want a smooth control move is what it's called there. But that essentially means we want to turn the wheel as little as possible for each control input, whereas we're still kind of getting to the right while we're still running the optimal path. And then the second goal we want to achieve is we want to have our path that we're drawing as close to the optimal path as we can get it to be. And then we got any difference between the path that we want to follow and the optimal path that we want to be on will be error, and then we can handle that error too. So both of the difference between the control moves and the difference between the path and some optimal trajectory are both errors, and we need to combine those errors and those factors to choose a path that basically minimizes both. And in order to do that, we need to set an importance to both. So say we're writing an MPC algorithm for a self-driving car that's driving a SUV that has a family in it, and we want it to be comfortable and a safe drive. We would be much more likely to weight the control moves higher than we would the optimal path, because we don't care as much how fast we're getting to our location as we would the car being a comfortable drive. So that would be one way that you could use weights. The converse to that would be we're trying to plan for a high speed race and nobody is inside of the car. We don't really care how comfortable the drive is. We just want to be as fast as possible. So we'll apply a much higher weight to the pathing and a much smaller weight to the control move. So those are kind of different strategies that you can use with weights. There's definitely also ways that you can run the algorithm with a variety of different weights and then try to find the optimal way to weight them for time. And that's probably the best way to calculate them. But depending on what your goal is with the MPC, you're going to try to decide weights in a different way. But that's kind of the goal of them and why they're so useful. And that's pretty much combining the weights, constraints, control horizon, prediction horizon, and then some sample time. You can basically generally understand the MPC algorithm and how all those kind of come together to minimize some cost function that considers a variety of different essentially things that would contribute to some goal state. So we want to basically utilize all these different things to find the optimal to choose an optimal path. Like you can see in the bottom picture, this optimal path is the black line out of all the different trajectories for car C on the right. So that's essentially what MPC will do. It will choose the optimal path using all of the different things that I just discussed in this brown bag. So that's kind of the general idea of MPC. You can go to the next slide, and I think there might be tools for how you can kind of play around with MPC and understand it a little bit better. Here, it's in our GitHub, the Wisconsin Autonomous GitHub. There's a point mass model. This actually was created by, this slide was created by Alex, one of our presidents, obviously. He made this, so he essentially saying, all he's saying is that if you look in our GitHub, under the brown bag tutorials, you can kind of see a MPC algorithm run, and you can kind of visualize it better. I'm not going to show it to you just right now, but that's available, and definitely a better tool if you're struggling to understand the concepts that I talked about in this video or in this brown bag. So that's that. And then last but not least, the last slide is going to give you a couple different links. So if you can get the slides for this brown bag, which everyone here right now has access to. You can click on these links if you're looking to learn more. And you can kind of gather a better understanding of MPC through these resources. And that's all for my brown bag. If anyone has any questions about MPC, the different design parameters that go into writing the algorithm, or if anyone's curious or wants to learn more, I'm working on an MPC algorithm right now with Raj, and I'd be happy to talk to anyone about this or answer any questions or anything. Obviously, there's more. This is a basics. This is kind of like the basics of MPC. It doesn't go into anything too crazy. Just kind of the general format of the algorithm. If you want to learn more, let me know. But besides that, I hope you guys learned something from this. And that's all for the brown bag. So thank you.
Awesome. That was great. Super interesting. Good work.
Thanks, Alex.
Yeah, I agree.
I have a quick question. You mentioned the impossible. Yeah, maybe I'll jump back. But you mentioned like that impossible situation where you can't satisfy both those constraints at the same time. And like, what have you found be like good ways to deal with that, or like in what ways can we as a team avoid that type of impossible situation?
So I guess the best way to answer that is the impossible situation, in the way I described it, is kind of just an explanation for why you have to use hard versus soft constraints. Going into any other time I've worked with constraints in the past, or any other algorithm that I've been using that like has required restraints, or any research I've done, all the constraints are hard. A constraint by definition is something that you need to constrain so that it can't reach a certain point. So it's pretty, the meaning of the word is pretty clear, and it makes it really misleading when you're working with MPC, because some of the constraints that you write have to be breakable. You can't satisfy every constraint that you put in every case scenario, and that's just the reality of the situation. And the best explanation for that, and the way I chose to explain it, was with the impossible situation. So just like in the picture below, like I explained before, you can't satisfy the constraint of the minimum speed and the gas pedal position at the same time. So because there's one situation that I can name, there's obviously infinite different ways that this situation like this can occur when driving in multiple different environments. But this is just one example. But because these impossible situations exist, we can't use hard constraints for every situation. A soft constraint, just like kind of I was saying before, is a constraint where that you can break if you need to. It's like please it's like a highly recommendation for the algorithm, and it's necessary for MPC. So as a team, if we're running into in the algorithm, but MPC is specifically where we run into impossible situations, our card might crash, or we might realize that we can't handle a certain situation. We might have incorrectly programmed at MPC and not included enough soft constraints, which instead of telling the car it can't do something, we highly recommend it that it not do something, and we give it the option to break it if it needs to. So that's essentially what a soft constraint is, and they're necessary for MPC. And the impossible situation is what will happen if you do not create good, like the required amount of soft constraints that you need to run the algorithm given your situation. So essentially soft constraints is the solution, would be the short answer to the question.
Okay, sweet. Thanks.
Yep. Any other questions from anyone?
Yeah, I got like two more, but they're more so about like how we use the controller for our team. So when you when you talk and like the objective function, what kinds of inputs do you need or are you expecting from perception or state estimation in order to make up those equations?
So the inputs that I'm expecting are obviously the barriers. So essentially we're gonna need the information we're gonna need to decide the constraints at every time step is going to be the barriers of the track, because obviously you need to stay within them. Those are hard constraints if that is intuitive enough. The obstacles in front of you, so other cars, maybe blocks that are put into the track depending on the competition that you're preparing for, or depending on what situation you're creating your algorithm for. You're going to need the location of the cars in front of you. So I'm expecting from perception, the boundaries of the track, the cars in front of me, and then those are probably enough. I think you would need a lot of information about the speed of the cars in front of you. Your algorithm can take into account, it uses a pretty dynamic physics model. I didn't get too much into the physics behind it because it's not too important in understanding just generally how the algorithm works. But I think given certain information about the speed of the car in front of you, the yaw angle, the direction it's facing, and other stuff like that, you'll be able to plan accordingly to constrain your car from not hitting the vehicle. That's important. Trying to think, other inputs would be the current speed and location of your car, because you're going to want to probably keep it above a certain speed. Say you're preparing for a competition. I think EV Grand Prix is like this. You need to maintain the minimum speed, or at least an average speed. So that could be a soft or hard constraint that you're using. So that's pretty important. So you're going to want to know the speed of your car, the location of it, and if you know exactly, I think state estimation would also be very helpful for being precise with that, because it's also very important to know the exact location. So aside from just the location of your car, the barriers on the track, and location of other cars, and maybe some other extra information about them, that's probably all you really need to satisfy the inputs for this equation. And then if it wasn't clear enough, the outputs of the equation are going to be a steering angle and a throttle speed, or amount to push down the gas pedal for every time step. It will be outputting one of those, and every time step it will be inputting the location of the car and all the other information I said before.
Okay, cool. Would we do overtaking within the MPC controller, or is that something that we would do separately and then feed that like decision making to the MPC?
Great question. I don't want to get too off topic, like talking about other algorithms, but if we were to use an approach that wasn't like MPC, what makes MPC so efficient is the nature of the algorithm, but it's a type of local path planner, which means we don't need a path around the whole track to follow. We can just create our own every time step given our environment. So if we had a global path to follow and we saw an obstacle in front of it, we would need to deviate from that path, and we would need to separate from the global algorithm. We would need to come up with a way to avoid an obstacle that we find at some random time in the middle of the race, say, or whatever your kind of situation you're preparing for. But with MPC, because we're coming up with an optimal solution every time step, We don't need to know any global path. We don't need any information about anything besides the current place on the track and the environment that we're in. And any changes to the environment at any time, because the algorithm is so quick and runs every time step, will be factored in immediately. And obstacle avoidance will be seamless, because the theoretical optimal path that the car would have chosen, given that the obstacle wasn't there, will be constrained against if it is there, because one constraint will be don't run into another car. So it'll take out all those path options, and it will consider and optimize the paths that don't hit the car. So what that will look like, it's kind of hard to visualize, but every time step, as it updates, it will just drive around the car in the most optimal way possible, and you won't need anything else on top of the algorithm to have to you don't need like another obstacle avoidance algorithm on top of MPC. It will do the obstacle avoidance for you, because of its nature and how it locally plans optimal paths quickly and efficiently.
Got it. Okay. Thanks.
Yeah.
My last question, and then I'm done. Is for the output of it. Like, do you think it'd be best for us to send that output directly to the actuator, or should we have like another layer of, I don't know, regulation between the MPC and the actuator?
I guess that kind of depends how you want to. I guess it's not really real. That's not really a question directly about MPC, because I feel like the MPC is in charge of getting that input and then outputting the values that are optimal for that situation. But I guess it is kind of about MPC, because a lot of MPC is a very is very costly algorithm. It is, in a lot of situations you just can't use it, because it requires a ton of computations in very little time, and if you're not making those computations quick enough, the algorithm will fail. So you need to be very careful about how you're handling memory, space, and then I didn't get too into it because it's a little bit more complicated than just for people who don't really know a lot about the algorithm. But there's a lot of different kinds of MPC that you can use to basically take away optimizations that it includes, to just so that you can have you can have it run efficient enough and not use too much memory, and basically allow it to be used. So I'd say, if you really require a third-party kind of algorithm or software that you want to run the inputs in before you take them to the actuator, that would be possible. But I'd assume that would take up more time than the algorithm's already taking. And because it's so important to run MPC as efficiently as possible in order for it to run as it should, you're not going to want to waste any time like that, sending inputs that are already finalized that could be sent to the actuator somewhere else first, even if you might want to check them and you may not have the best estimation system. So maybe you might want to check the outputs and change them with some other algorithm. I don't know. I don't know what you would have in mind, but whatever is the fastest you're going to want to do. And I'm assuming that would be sending it straight to the actuator. So that would probably be what you would want to or have to do in order to run that algorithm fast enough. That would be my answer. But again, that's a little bit outside of the actual algorithm being run. So it would be up to like the user, but that would probably be my recommendation.
Okay. Awesome. Thanks.
Yep, of course.
Sounds good. Yeah, thanks, Evan. Really good presentation. Anybody else have any questions, or are we good to go for today? General questions too.